Let's start. Good morning, good afternoon, and good evening, depending on where you are. My name is Soumitra Das. I am president of Healthy Climate Initiative. Before we start, I have to make an apology for those who are following Indian Standard Time. When I set up this webinar, the time in the US changed by 1 hour. And I did not count for that. As a result, when I set it up 8:30 p.m. for the Indian people or people who are following Indian time, it has changed to 9:30 and I did not count at that time. So I'm very sorry for those who had to wait 1 more hour. Hopefully you were able to get my email and saw the message when you logged in that it was going to start at 9:30. With that message, I want to introduce the agenda before, and after that, I'm going to say a few words about HCI. After the introduction, my introduction, we'll present a short video that highlights the methane problem by Sir David King. Then we are going to move on to the main program, the need for methane removal webinar, and it's structured as follows. Dr. Susan Lee will introduce Peter Fiekowsky and Kevin Lester, who are our esteemed speakers today. They will each give 5 minutes presentation. It will be followed by question and answer session, which will be moderated by Dr. Susan Lee. And then we'll open up the floor for the audience, question and answers. Please send your questions via Q&A window. And then we'll move on to concluding remarks by me. Just to say a few words about the video. It was presented by Sir David King, whom you are going to see in the video. Sir David King is one of the most important figures in the climate change movement. He is an emeritus professor in physical chemistry at the University of Cambridge. Previously, he served as a chief scientific advisor to the UK government under both Tony Blair and Gordon Brown, and head of the Government Office for Science. In that time, he influenced the government to act on climate change and was instrumental in creating the £1 billion Energy Technologies Institute. He was knighted for his work in 2003. We present this video to set the stage for the webinar. Now let me say a few words about Healthy Climate Initiative. About HCI, it's a non-profit organization to combat climate change. Our mission is to restore climate and make it safe and healthy for future generations. We have undertaken several activities. Just want to highlight our internship program. We recruit summer interns for high schools and colleges to work climate change. The goal for this program is to create youth leaders for climate change. Currently, we have several dedicated interns working on climate restoration projects from the US and India. We plan to expand this program on a larger scale next year. Other things we have been doing is the webinar. The webinar is just not about imparting some information to you, but also take this webinar so that you take this the knowledge and the lessons and tell few more people, 5 people, your neighbors, your friends, your relatives. And this is how we can start a movement and change the current policies. And that's what we are hoping that you will contribute to this movement. For more information, please visit sci.in.net. And to become a member, please contact Mr. Chandan Bhattacharya, CK Bhattacharya at 1963@gmail.com. And for those who want a certificate for attendance, please contact Mr. Chandan Bhattacharya at 1963@gmail.com. With that, I will hand over to Dr. Susan Lee to start the session. Thank you. Thank you very much for attending this webinar.
Okay, so I think
Susan,
next is
over to you.
video, Sir David King video.
All right, yes. Very good. So let me start the video. Taking a little time to set it up.
How many sessions on? If you can close, but it's not required.
Yeah, because
We have opened too many applications.
my apologies taking longer than
Well, I could get started on the overview while this is starting. Shall I?
Yes, I think that's probably a good idea.
Why don't I introduce the speakers first then?
Great.
Okay.
Let's see. It looks like the video is coming up though. So let's see if it works.
Yeah, and let me go to the. I think you start the because
Yeah, it'll take you a minute to find the location.
Take a minute.
Okay, so
Maybe you can start the.
I will go ahead and do the introductions. Okay. Thanks everyone for being here. I first want to introduce our first speaker, Peter Fiekowsky. Peter is a visionary, a serial entrepreneur in the area of climate restoration. He's the co-founder and chairman emeritus of the Foundation for Climate Restoration. He is a MIT trained physicist, an entrepreneur with 27 patents, and he is also the founder of an international network of atmospheric methane removal scientists and experts. So I'm thrilled to have him speaking to us today. And in addition, I'm also delighted to have Kevin Lister. Kevin has over 30 years of experience in climate change research. He has advised politicians on NGOs on climate policy. In 2018, he coordinated a major submission to the 2018 United Nations Talanoa Dialogue. And Kevin serves as the president of Restore Our Climate, a nonprofit organization working to develop the science of iron salt aerosol. Yep. I also want to take a moment to give special thanks to Julia Dieterer for her leadership in the climate restoration movement, and also for her work in making this webinar possible. Okay, with that, I'm going to turn it over
Sumitra, is the video ready or shall I get started?
Let me get the video. Okay, I think you get started and then I'll get back to the video.
Okay. Okay. So I'm going to start out, what I'm going to spend a few minutes talking about is what is climate restoration and why do we care? And what do we do about it? And then especially, how does it relate to methane? This is not a chemistry report on methane. This is about you and your children and humanity's future generations. So here we go. Good. So we have the slides coming. And so climate restoration is about future generations. When I got involved in the climate, I was asking the question while looking at my mission for my personal mission, which is to leave a world that we're proud of for our children. And when it came to climate, I was very clear that the way things are going, I would not be proud of where things are going. So I asked, what is it we want to achieve? And as you can see here, climate restoration is the goal of restoring CO2 levels to what they were during the formation of agriculture and our civilization. And so if you're a scientist or an engineer or a manager, that means getting CO2 below 300 parts per million. And anything below that is levels that humans have lived through long term. You may know that today we're almost 50% above that. And I think all of you, everyone listening to this now and in future weeks and months, have become very aware that indeed our ecosystems and our climate systems are breaking down, pretty much as expected. So climate restoration can be achieved using existing solutions, and those solutions are modeled on how nature has removed the trillion tons of CO2. Nature has done it 10 times in the last million years. Now, we're not going to be discussing CO2 removal today. I just want to leave that. If you've never heard that assertion, it will have you return to future webinars. And today we're going to be talking about methane. So methane is a greenhouse gas, so it's like CO2, and it's over 100 times more potent in terms of warming the planet. What's interesting about methane is it's different than CO2 in that it doesn't live in the atmosphere for very long. It has a half-life of 8 years, which means that after 8 years, any methane that comes out of a landfill or a gas leak, that will have oxidized down to half of that will have oxidized in 8 years. And so what that means is that although methane absorbs a lot of heat and provides an enormous blanket, it's fairly easy to deal with because it does oxidize. And that's the basis of most of what you're going to hear in the next 45 minutes. Let's go to the next slide. So methane has sort of an urgent aspect to it, and that is a methane burst that may be starting now. And in the East Siberian Sea, there's permafrost. There's a frozen layer on the seafloor, which is only 50 meters deep, from 0 to 50 meters deep. And as the sea ice melts, that frozen seafloor is beginning to melt. Just the same way that if you have a soda with ice in it, the soda stays cold as long as there's ice floating, but once the ice melts, then the soda warms up. The same thing is happening in the Siberian Sea. And Russian scientists have seen the methane beginning to escape from that frozen seafloor. So let me go back now to the next slide and go to the bigger picture. So this is what got us alarmed. So in terms of methane on the planet, this map makes it look like there's very little in the southern hemisphere and there's lots in the northern hemisphere. In fact, from the darkest blue to the darkest brown is about only 10% difference in methane concentration. And so you can see two things on this map about methane on our planet. One is quite uniformly distributed. And the other is the dark areas are obviously where, well, for me, obviously, I apologize, I do that. The dark areas are where the methane is being emitted, and then it gets diluted in the other areas. And so you can see South America with all the rainforests and livestock is a big source. You can see that China with the enormous rice fields, when the rice is turned over in the winter and it starts decaying, that produces enormous amounts of methane, as you can see on the map. And you can also see in the permafrost areas, a lot of methane escaping. And one of the conclusions I want you to draw from this is that when we try to reduce methane emission, it may be a fool's errand because we probably cannot put plastic wrap over all of South America and over much of China to hold that methane. That's a bit extreme, but I think you can see the point that if we're going to deal with the methane, we're not going to be able to stop it emitting significantly, but we can double the nature's method, which is to oxidize the methane. So we'll go to the next slide.
Peter, you have just a minute or so.
Okay. And so when we look at the methane, we look at it, there are two main issues. One is what we call the chronic or gradual methane increase. And on the graph here, you can see methane has pretty much tripled in concentration since the beginning of the Industrial Revolution. In the beginning, it started as emissions mostly from coal mines. As you can imagine, coal essentially is semi-decaying vegetable matter. So there's enormous amounts of methane coming out of coal mines. And then in more recent years, much of the methane has come from fossil fuel production, livestock, and landfills. And as you saw on the map, accelerating the natural methane oxidation appears to be the only viable solution, which really has not been discussed until now. So you're one of the first audiences to hear about this. Next slide.
Okay,
now,
Peter, can you wrap up in just a minute or so?
Yeah.
Thanks.
And so the other aspect of methane is what we call a methane burst or the acute. And that the issue here, that this graph is a bit too complicated to explain in 1 minute, but some of you may have seen something like it. This is CO2 over the last 500 million years, and time is exponential. And so it's a little hard to grasp. The main point is that CO2 levels today are fairly close to what they were during the dinosaur age. So T-Rex would like today's CO2 levels, and there was no ice cap then. Today we're transitioning to an ice-free Arctic. I'm sure you've read the news. And so the last time our planet did that transition from having occasional occasional ice ages to no ice, we had an extinction event where there was a burst of methane. And so the technique we're going to discuss a little bit, similarly, can let us deal with that burst and avoid a potential extinction event. There's no knowing if and when it will happen. We only know that the last time our planet went through this geological phase from ice ages to no ice ages, to no ice in the Arctic, we did have this burst. And from there, I'll turn it over to Kevin, or to Sue to turn over to Kevin.
Thank you, Peter. Okay, I think this is
I'll try the video this time, see if it works.
You want to try the video? Okay.
Let me try. Okay, let us try again. Hope this works.
Okay, can I? Oh,
Yeah, here we
is it
go.
working?
I think the
I
bandwidth
think-
is not going to work.
Yeah. Why don't we take
Video's
this
not
time-
working.
Yeah.
Why don't we take this time and have Kevin do his presentation? So
Okay, let us do that.
let's switch to Kevin's slides, and I will turn it over to Kevin.
Thank you, Sue. Thank you, Peter. And thank you, Sumatra, for inviting us in to give this talk. And if we can have the slides up, and we'll talk through. Thank you. And can we have the slide show up as well and get the full
Yeah,
click in the middle at the top.
yeah, let me do that. Yes, it's working now.
Okay, thank you again. So I guess the first thing I should say here on the title, understanding the methane emergency. I think, thanks to Peter, he's really outlined just what this methane emergency is. And I think what I want to do is talk about how we can address the methane emergency as it is currently starting to develop. So on to the next slide, please. Let me just overview what we're going to be talking about in the next 5 minutes or so. So this is what I want to cover. I want to talk about this idea of iron salt aerosols and how we know it will work. And this dovetails into Peter's comments that what we need to think about now is how we can oxidize methane out the atmosphere and how this is such a critical aspect of our response to the changing climate. We know it's going to work. We're pretty confident of that. We need to quantify that. Again, we'll talk about that. Having established that, what we then need to look at is a strategy for dispersal, which we're going to talk about, the time scale for testing and implementation. And then I want to just open up more generally on the risks of doing something versus the risks of doing nothing. And there's been a long and ongoing debate in environmental circles about the concept of intervening in the climate system. There have many people, many NGOs, many governments, many climate change activists, many climate change scientists, many people of eminence arguing that we should not intervene in the climate system and that we are playing God in so doing. But what I do want to argue and kind of close out on the talks is that risk balance. What's the risk of doing it versus what's the risk of not doing it? So let me move on to the next slide if we can. Okay, so what is iron salt aerosol and what does it do? So when we talk about iron salt aerosols, we're really talking about a couple of things. One is the idea of using ferric chloride, so it's iron chlorine 3. The other one is iron nanoparticles, which you can disperse over the ocean and that will react with the ambient hydrochloric acid that's actually in the atmosphere and comes from sea salt. But basically on this top diagram, coming in on the left-hand side, you can see that there's a little arrow for methane. And essentially what happens is that the the iron particles will tear off the hydrogen atom from a hydrochloric molecule, leaving a chlorine atom, which is in the top left of the diagram. The chlorine reacts with the methane to pull off a hydrogen atom, and then the hydrogen atom or the hydrochloric acid comes back into this particle, and a catalytic process develops, which is driven by ultraviolet radiation. So essentially what happens with methane, when methane's in the atmosphere, it gets reduced down to CO2, and this is the thing coming out at the top left of the diagram. So methane gets reduced to CO2 in two ways, either by hydroxyl radicals or by chlorine. And the chlorine is much more powerful as an oxidation tool than the normal hydroxyl radicals. So typically what we think is that, and the calculations so far have shown that the iron salts can react with methane about 16 times faster than normal natural methods. Yeah, that's kind of at worst, but at best case, if we've got the right levels of humidity, then that rate increases to about 32. So the question then is, well, what effect does that have on methane? Well, the diagram that I've shown here is from the IPCC report, from IPCC AR5. And what this shows is basically the radiative forcing of a molecule of methane or from a pulse of methane over a period of time. So initially, you start off with methane about 120 times more global warming potential than CO2, and that decays in an exponential curve. Now, if you can reduce basically the half-life by a factor of 16, because of the exponential relationship, this curve gets effectively squashed into the left-hand axis. And the thing that we're really interested in is the area under this curve. So by reducing the half-life by, say, a factor of 16, this curve gets absolutely squashed into the left-hand curve, and the area under the curve diminishes significantly. So that has a major reducing effect on methane's ability to perpetuate global warming. On the other hand, if the half-life of methane increases, and it's likely to do so if the concentration of methane increases, then the curve gets stretched out to the right. And again, this area under the black curve then increases. So the shape of this curve, because of its exponential characteristics, has an enormous impact on the warming effect that we get from methane. And basically what we're trying to rely on is this photocatalytic effect, pulling this curve significantly towards the left-hand axis. Okay, on to the next slide. So in terms of, do we know this is going to work? Well, there's really no question about the photocatalytic effect happening. We've done extensive literature reviews. We're working with some of the world's best atmospheric chemists, and there's numerous natural analogs. So we know the process works. What we don't know is how fast it works, and this is the stage of the project that we're now moving into. So what we really need to know for the next stage is accurate quantification of those factors that will affect the reaction rates. And there's numerous factors. There's humidity, the ambient hydrochloric concentration in the atmosphere, there's the actual methane concentration, particle size, and so forth. So we've now started experiments at Copenhagen University to start the quantification of those factors on the reaction rates. Okay, next slide.
And Kevin, if you could start to wrap up in the next minute or so.
Okay, will do. Okay, so very quickly, there's the experiment. It's kind of what it looks like. We have a lab air coming in. We have basically the lab air with the methane coming in. We have the iron salt at the top, and we have a reactor chamber. And on to the next slide, a quick picture of the actual experiment. And this is what the experiment's looking like in real life. And very quickly on to the next slide, just to give you a flavor as to where we're actually up to. So the experiment is now set up, and the experiments are pretty much starting as we're talking at the moment. Move on to the next slide. Okay, in conjunction with experiments, what we're also doing is setting up a geochem model. So once we know what the reaction rates are, we can then model the changes in the atmosphere based on the methane emissions and the iron salts. And there's some big questions that we need to answer here. So two big questions is, where should we best place the iron salts for distribution? Do we do it near the methane sources, or maybe over the ocean regions? And how much iron salt aerosol do we need to disperse to get a given amount of global cooling? So that's the next big thing that we're doing in parallel with the experiments. On to the next slide. Next slide.
Sorry.
Okay, quick overview of the time scale. We are in a rush. If we can go to the next slide.
This
Okay,
one.
so, yeah, that's the one. Yeah, so we are in a rush. We are doing experiments up here, the smog chamber tests, the atmospheric modeling, and ideally what we want to be doing is we want to be starting field trials next summer. And the thing that is ultimately determining our program is the speed with which the Arctic is changing. And as Peter was talking about before, we are transitioning into a hot house Earth condition. Once we get into that case, then it will be impossible to reverse back. So that is our defining limit on time. On to the next slide. Okay, now again, just talking about the risks, the risk of do something versus do nothing. And the general approach being taken to climate change so far is that we somehow reduce our emissions and that the world will stabilize. And that's clearly not going to happen. So the risks associated with climate change, as I say, are too serious to ignore. Again, just to put things in perspective, last time atmospheric CO2 was at 400 parts per million, sea levels were at least 20 meters higher than they are today. And there's continuing intense upwards pressure on CO2 emissions. Heat waves are already destroying the ecosystems, and the political and economic systems globally are under incredible stress and more likely to break down. So everything is pushing against us now. So the risks, we would argue, with starting small-scale field trials and starting to build up gradually are far smaller than the risks of doing nothing. On to the next slide. I think that kind of takes me down as I'm running down towards the end of time. Quickly onto the next slide. Okay, just very quickly, other comments on IPCC. Sorry, up a slide. Just to close off. Previous slide, please. Yeah, very quickly, comments on the IPCC. They've already started moving towards thinking about methane. In the special report, the IPCC made clear that the permafrost is starting to melt, and also made clear as well this other critical factor that though CO2 dominates long-term warming, one of the quickest responses that we can have to the climate crisis at the moment is to remove the short-lived climate forces like methane. So effectively, methane contributes at the moment about 30% of the radiative imbalance of the atmosphere. And for us to reduce methane, to limit that 30% addition, we can do so much quicker than removing an equivalent amount of CO2. Okay, last quick slide, and this is just a quick one on what to do to get involved. And jumped over one. Oops, up. There. Okay, again, so you can help. Visit our website, restoreourclimate.earth, and we need people to help at the moment, modelers, chemists, toxicologists, and so forth. So you can contact us through the website here, restoreourclimate.earth. Thank you. Appreciate I've gone slightly over.
Thank you, Kevin. Okay, great. So let's start our question and answer session. I'll read the first question and then I'll ask each of our panelists to answer it. So the first one is, climate change seems incredibly complex. We've just seen a lot of information in a short time. Is there a simple way to understand the problem and the solutions? Peter, could you take that one?
Yeah, the simple way to look at the climate change is it's triggered by CO2 emissions. I think that everyone has heard that. And the best way to see the solution of climate change is to bring CO2 back to the levels that we had in that 10,000 year period when agriculture and civilization developed. So it really is that simple. In terms, if you're predicting the future, the scientists like to look at temperatures, but if you're trying to restore the climate, you just look at the CO2 level. And then the methane is related. And yeah, I think I'll just leave it at that for the moment.
Okay, so what I'm hearing is that even though it's incredibly complex, we can look at it as a physical problem with two things to look at: CO2 concentration and methane concentration, and that simplifies it greatly for us.
Yeah, actually, a good way to say it is, if most of us have been in a hothouse and it gets very warm, and if you open up the window in the hothouse, it cools off. And that's what we need to do, is take off some of the glass from the hothouse to cool off our planet.
Great, thanks. Kevin,
I do have a question here, because one mechanism still not understood by me. In atmosphere, the presence of the hydroxyl ion, maybe with extra electron in it, that becomes a sink for the methane.
Yeah.
So what exactly is the mechanism that is basically regulating the methane? But this is optimistic viewpoint is given that if you increase this, the hydroxide, in the upper atmosphere, that can become as a methane sink. So presence of the hydroxide, how it happens and what exactly is the mechanism? Do you have any glimpse of this? But this mechanism needs to be understood if you're really talking about the, this atmosphere to act as a sink, because extracting the methane from the atmosphere is next to impossible. Because of the very trace amount available out there. Unless we get the source, we can't really extract methane from atmosphere unless we use the hydroxide as a methane sink out there. Can you enlighten me on this point?
Yeah. So yes. So the hydroxyl radical, as you say, is already acting as a sink for methane, and the hydroxyl radicals are formed naturally in the atmosphere as UV comes in and strikes water molecules and methane. So that's a naturally occurring process. There's so much hydroxyl radicals, and those hydroxyl radicals, as you say, currently oxidize methane down to CO2 and water vapor. The problem is that there is not enough hydroxyl radicals to catalyze methane or to reduce methane quick enough. What we are advocating is increasing the chlorine content in the atmosphere, or the available chlorine content in the atmosphere, and that's partly done by using the existing hydrochloric acid that's naturally occurs in the atmosphere to increase the size of that sink for methane. And what we find is that you only need a relatively small amount of increase of available chlorine to significantly increase the sink for methane. And as I was trying to allude to in the slides, if you can reduce just for a small part the half-life by effectively a factor of 16, then that has an enormous impact on the overall methane climate forcing. So what we are advocating is increasing that sink of methane.
Okay, great.
I think just coming back to Susan's point and just reiterating what Peter was saying about is there a simple way of understanding climate change? I think one of the simplest ways is understanding your own body temperature. That, my body temperature is, I don't know what, it's 36.4 degrees. If it gets to 37, I am extremely hot. If your body temperature rises 1 degree or 2 degree, then you're getting into a point of danger. If your body temperature rises like 3 or 4 degrees above normal, then you're pretty much dead. And it's not that dissimilar to the Earth. When we talk about the global climate increasing by 2, 3, 4 degrees, when we get to 4 or 5 degrees, pretty much the ecosystem collapses. And what we argued in the Tanaloa dialogue, and to me, what's the big motivation for me behind all this, is what is a scientifically set safe temperature target? What's a safe temperature increase that the Earth can have? And what we argued was that the maximum safe temperature rise can be no more than 0.5 degrees C above baseline, because that was the point when we first saw interacting feedback mechanisms being triggered. So to me, one of the big measurements of climate change is what is the safe temperature target. And that has been something that's really been missing in much of the discourse on climate change, certainly in the COPs and the IPCC.
Thanks, Kevin. I want to move on to our second question. So first, we've all heard that humanity needs to limit the worst effects of climate change, to reduce emissions of CO2 and to reduce emissions of methane. Are these useful goals? Let's start with Peter on that one.
Oh, it's a very difficult question. When I was an undergraduate 50 years ago, it was definitely a useful goal. So in 1975, reducing emissions could have stopped the global warming problem. 50 years have traversed, and it's now really too late for reducing emissions to save us. So fortunately, emissions are trending downward. So in Europe, almost half of electricity is renewable. Soon the same will be true in the United States. I think India is also accelerating very rapidly towards clean energy. So that transition is happening anyway. But if we want to survive, and of course we do, then we need to get CO2 levels down. So our focus needs to be on getting CO2 down and temporarily on getting methane down to avoid the gradual increase, which is, it's gone from 20% to it's now almost 40% of our heat is from methane. And as Kevin said, getting rid of that methane is very viable. We're working on it. We're going to do it, and every bit of support we get to make it happen faster will be useful. And the same will be true of the CO2. We know how to do it. We just need to really, for people to encourage our leadership to say that what's important to us is the survival and flourishing of humanity. Now, traditionally it was about emissions, but really most of us care that our children survive, and emissions are a secondary issue. So it's turning that around, focus on our survival.
Thanks, Peter. Kevin, would you like to weigh in on that? Why is so much attention being given to emissions reduction?
Emissions reduction is essential. It is absolutely essential that we get emissions down as fast and rapidly as we can. And the graph that has always terrified me was something I realized a number of years ago when we put the Tanaloa paper together. And what we did was we plotted the cumulative fossil fuel emissions against the Mauna Loa CO2 concentration. And what we found was a perfect straight line correlation. That if you imagine the cumulative emissions on the x-axis, the CO2 concentration on the y-axis, and we plot one against the other. And the correlation was, the R squared for the correlation was 0.999507 or something. It was ridiculously strong. And what that indicated was that the natural rate of CO2 emission in the atmosphere is virtually zero. The natural rate that the environment can remove CO2 from the atmosphere, it's virtually zero. It's almost not measurable. So everything that we put into the atmosphere stays there, either stays in the atmosphere or in the oceans or in the ecosystem, isn't it? There's a natural flow between all of those reservoirs. But everything that we have put in the atmosphere is still in the atmosphere. everything that we continue to put in the atmosphere will stay in the atmosphere. And we are already at 400 parts per million. We are already well and truly into just into the most unbelievable danger zone. As Peter says, we are pushing hard in terms of moving towards renewable power, but we still have huge CO2 emissions ongoing. We absolutely have to crash those down as fast as we can. But even if we can get to zero carbon tomorrow, it's still not enough. And what Peter is doing, what I'm doing, and what this conversation is about is what comes next and what else must we do. And the upper pressure is continuing on CO2 emissions, unfortunately. We have an emission trajectory that is going to take us to somewhere near 4 or 5 degrees Celsius. And coming back to the simple understanding of climate change before, we are not going to survive as a civilization at 4 to 5 degrees Celsius. We need to find ways of cooling the planet now.
Okay, let me go on to the third and the last of the moderated questions. And that is, with the benefit of foresight, what's the responsible thing to do about atmospheric methane? What do we need to accomplish and by when? And Kevin, would you like to take this one first? Yeah, so at the moment, let the figures speak on the argument. So we are around about 1,815 parts per billion of methane. We started at the Industrial Revolution at about 800. So we are already firing well into hugely elevated levels of methane. We already know that the energy imbalance of the planet is something now that is unsustainable. So that now is a moral imperative to start finding ways, testing ways, developing ways, building the logistics and methods that can start removing methane from the atmosphere as fast as we can. There's just not time to waste any further. We've got to hope that this is going to work. We're confident in the science, but we need to calibrate it and we need to start pushing forward. And we need governments, we need policymakers, we need a dialogue and discussion to help push these kind of arguments and processes forwards. Great, thank you, Kevin. Peter, would you like to weigh in on that? What do we need to do about methane and by when?
The model for change for action that I use is that if I want to do something, the first thing to do is to figure out the outcome. And so just like with the climate, climate restoration is about restoring the climate, having the climate be the same way it was. And as you can see in our discussion, there's still a lot of concern just for emissions, whereas most of us humans really want to restore a safe climate. The same is true for methane, that it's very important to do the research and so on. But the first thing needs to be that we want the flourishing and survival of humanity. And that means that we need to have the insurance. Once you decide that that's important, and that's not public, right? You don't hear that in public yet because that's never needed to be said before. But now that our ecosystems and climate system is collapsing, we need to say that for the first time. So that's the first step, is to say we actually want the flourishing of humanity. And then the next thing immediately is an insurance policy to remove the methane. Now, yes, nature knows how to do it. And yes, engineering will help us amplify nature's capability. The first step, say it the third time, the first step is to decide that that's our goal, because our leadership can't say that without us encouraging them. So I think, Sumitra, thank you for these seminar series. The whole purpose of this is to create a certain groundswell of voices telling leadership in India, in the US, in the UN, please make our top priority the flourishing and survival of humanity, and then worry about the technical details.
Great, thank you, Peter. Okay, so we're getting close to the top of our hour, and I want to announce that our speakers have been willing to stay after to continue the Q&A session. So Sumitra will explain to you how to do that if you have time to stay on longer. Sumitra, do you have a question from the audience that we can ask to our panelists?
Yes, there are quite a few questions. And let me start with the one from Harp Simmons. His question is, can you address the so-called moral hazard that removing methane will give people license to ignore reducing methane emissions from livestock and fossil fuels?
Great.
I'll take it.
Peter, go ahead.
Anyone want to take that question?
I can take it. Peter can take it. I think we're both of like mind on this one. Do you want to take it first, Peter, and I can come in afterwards?
Sure. So it's like CO2. The first thing is to keep the boat floating. So I like the analogy of, imagine a wooden ship which is beginning to leak water in, and then you have pumps. You can pump the water out. And a lot of people say, well, don't pump the water out until you fix the leaks. You got, a good ship owner will fix the leaks first and then pump. Well, if the boat's sinking, pump the water out. Doesn't matter about the leaks. And that's true of CO2. That's true about methane. Handle the methane and worry about the leaks later.
Okay, I would answer, and I saw the comment coming up in the chat saying, well, should we just let gas wells flare away? The answer is clearly no. I mean, what we need to do is we need to get methane down, not just to pre-industrial levels, but potentially below pre-industrial levels. So, my target would be somehow to try and get methane right the way down to maybe 400 parts per billion or 300 parts per billion. We need to do every single thing that we can possibly do on methane. And that would include making sure, as a first point, that we stop any extraneous methane releases that we can stop. But even if we stop all the gas wellhead leaks, and we need to do that, then there's, as Peter said, there's still methane coming from other areas that are just really much more difficult to try and address. So agriculture, there's the warming of wetlands, there's rice production. There's just so many sources now of methane, and obviously there's the big issue of the permafrost. But at the end of the day, we need to be conscious of targets. We need to have the right targets. The right temperature target, as best as we can see, is a temperature rise less than 0.5. That means being extremely aggressive on tackling the methane sources and extending the methane sinks, which is what we are advocating. And this extension of the sinks that we are advocating for methane is not yet part of the common discourse on the global approach to climate change.
Thanks, Kevin. And thanks, Herb, for that excellent question. Now, since we're getting close to the top of the hour, I want to make sure that we at least formally end the webinar on time. And after that, we can all stay around and join the encore session for further questions and answers. So let me turn it back over to.
Yes, thank you, Susan. So we plan to end the webinar session at 11:55. I mean, depending on where you are. In the US, it's 11:55 Eastern time. And but the speakers are willing to stay another 10 to 15 minutes. So if you have more questions, we can go on to 10, 15 minutes on answering questions. So Susan, with that, looks like attendees are still there. So let us go ahead and ask questions.
Wonderful, wonderful. Let's let me ask you, Sumitra, to give us a question from the audience.
So this question comes from Julia. She's asking, landfills have been identified as a C4 source. I assume C4 means methane here. Have you prioritized a program to address landfill methane or C4?
Okay, who would like to take that question?
I
didn't quite catch the question. Can you just repeat that again?
Landfills have been identified as a C4 source. Have you prioritized a program to address landfill C4?
I'll get started with that. So again, with the boat analogy, imagine a wooden boat with the slats and water leaking in. One of the sources of water leaking into the ship to sink it is landfills. Rice fields are others, agriculture is another, fossil fuels another, permafrost is another. Obviously, it's good to have people patching the leaks, but if you want the boat to not sink, you got to pump it out. And so for me personally, given my commitment to future generations and my kids and your kids, I'm focusing on pumping the water out. I'm focusing on the methane oxidation. And it's great to do all the other things. But if you don't get the methane reduced, which is pump it out, oxidize it, we're likely to not be around by the end of the century.
Yeah.
May I just comment one point in respect of the landfill? Is it not the chemical fertilizer which has been used over the years, actually, that is bringing the higher level of the nitrogen presence in the soil? Like in cases of the rice cultivation and all this, we all know that this is one primary sources of the methane. But methane is not totally unneeded in the atmosphere, but this was in the balance, because otherwise world would have been much more cooler. So correct balance is okay, but what happens because of the imagined fire burning, also rampant cultivation of the animals and all those things. And we all know that because of the animals, this belching out and eructation that is causing this methane, and now new advice and being given that the people should go in a vegetarian way and eat less meat for the sake of the climate. But I feel that chemical fertilizer have done a great harm. I think whoever the intelligent person has invented it has done the maximum damage to the environment. This is, apart from the land degradation, this is another cause for the this leakage, as you are saying, the methane. Do you see eye to eye with me, or you have got a different take?
Who would like to take that one?
Can you summarize the question, Sue?
Yeah.
I mean, what I mean that the presence of the nitrogen in the soil, particularly because of the chemical fertilizer, has caused the this methane leakage problem more prominent. Is it a fact?
Okay.
Yeah, I was going to say, I'm not an expert on the chemistry of soil, but I'm aware of the issues that you are describing. And it's a bit like what Peter was saying earlier on. If we could go back in time 50 years ago and stop CO2 emissions, then we wouldn't be perhaps in the predicament that we are. What we have done across the world is we have changed the soil chemistry with huge quantities of fertilizer. We've changed the whole ecosystem. And almost whichever way we cut the dice, we end back in the same problem. So we can say, well, perhaps everybody should be eating less meat, and therefore we have less methane from cows. And we say, okay, well, that's fine. But that gets everybody eating more vegetables and more rice and more wheat, which has its own sources of methane, as you're alluding to, with the changes to soil chemistry. And it's like one of these awful situations that we have now created, and there really is very few clean exit routes from that. And again, it comes back to Peter's analogy. We need to start getting some pumps running now. There's some holes that we can patch up, so wellhead leaking, maybe some landfills, and we should patch those holes up wherever we can. There are some holes that we just do not know how to patch up, and it's unlikely that we'll ever see a solution anywhere in the near future. And because of that, and exactly for the dynamic that you just described, we need pumps. We need some big, powerful pumps, and we need to know what the capabilities are of those pumps as well.
Very, very well.
So next question goes to next question. It is coming from Daniel Galporn. As question goes to Kevin. Your target is 0.5 degrees centigrade. north of baseline? By that, do you mean above pre-industrial temperatures?
We mean not, well, 0.5 above the pre-industrial temperatures, exactly. So that would be the temperature round about 1980. And the reason that we choose that as a temperature was, and in 1980, three things were observed for the first time. So we started seeing the measurable reduction of Arctic sea ice. And that was Peter Wadhams was the first person to start recording that and concluding that that was most likely due to warming of the planet. The other thing that we saw for the first time in 1980 was the wide-scale bleaching of coral reefs across the whole planet. And at the time, there's all sorts of debates as to what was causing that. There was debates, it could be a virus, it could be pollution. And Tom Goriot, who worked with us on the Tanaloa paper, put down at the time that that was actually due to warming of the ocean surface. The other thing that we started seeing around about that same time was the first releases of methane from the seabed, or new releases of methane from the seabed. And that was Jim Kennett that started spotting that. So these are three amplifying feedback mechanisms which all interact. So at 0.5, we were starting to see instability in the climate system. You know, the dice was already cut in 1980, around about 0.5. So presumably the safe temperature rise must be less than 0.5. It cannot be 1.5 that is the current COP target. The 1.5 is just a politically set value. There's no science behind that whatsoever. So yes, we mean 0.5 above pre-industrial baseline. It's this analogy that I drew earlier on about your body temperature. You know, when your body temperature gets above 0.5, you're starting to get into problems. If your body temperature gets 1.5 above normal, then you're starting to get into serious problems.
But going by the IPCC's report, 1.5 is a very too much optimistic dream. Even they're saying that we should be prepared from as high as 2 degrees and beyond, even 4 degrees. That's the IPCC is telling. That means the ocean water warming is already, coral bleaching is happening, as you are saying very rightly, particularly in the Great Barrier Reef area. Some people have, of course, postulated that it may be because of the chemical people use during sunbath and all those things. But it is right now, I think, established. This is the warm temperature that is causing the coral bleaching. It happened in Lakshadweep also, where people are not using. So it is correlated right now. That is because of this warm temperature. So we are already getting a sign of primary sign of the extinction of the marine creatures, and it is going to be a big food crisis all over. And recent information is that China is already witnesses a major food crisis. I think the whole world should be prepared for that.
Exactly. Yeah, and that's happening at 1.2 degrees above baseline at the moment. A sustained temperature rise from 1.2 to 1.5, and the longer we stay at 1.5, the more accumulated damage that we get under the curve. You know, we are struggling now at 1.2. We're not going to be able to cope at 1.5. 1.5. We're on track to 20 meter sea level rises. We're already on track to 20 meter sea level rises now.
Can I bring in a perspective here?
That 1.5 degrees Celsius is not a reasonable target at all. And I'd like to ask Peter to weigh in on temperature targets and what we should set as goals, whether they should be temperature targets or something else. Peter?
Yeah, thank you. Yeah, you know, the half degree of warming that Kevin discusses corresponds to the 350 parts per million that Dr. Jim Hansen has been promoting as a goal. And you know, the idea of that is clear that above that heat level, massive ecosystem collapse happens, and we won't survive, unlikely to survive well. And that's sort of the 50%. And so I have a horrible analogy of playing Russian roulette with our children. So the half degree is sort of like half the barrels, maybe 3 barrels have bullets and 3 don't. and we'll see what happens. Of course, we don't want to play that game. We want to give our children a future with all the barrels empty, which is putting the CO2 back to levels that we always had. Now, it is true that there's a good chance at 350 parts per million or half a degree, there is a good chance that we'll survive, but that's not the game we want to play. Let's not play that game. That's a statistics game, which is good, but a lot of us are parents and uncles and aunts and grandparents. I'll be a grandparent next week, I think, for the first time. Let's play the game for 100% chance, which is putting the CO2 back to the way it was. And it's hard because the whole climate community has adopted the, maybe, it's horrible to say, but if 350 parts per million is 3 barrels empty, then 2 degrees is maybe 1 barrel empty and 5 barrels with bullets. And that's just insane. And I assert that it's just a matter of not reevaluating after the mid-70s when this became alarming. In that, as I said, in the mid-70s, that was a good goal of zero emissions. By the time this was a big deal in 1988 when Jim Hansen addressed Congress, we were already past 350. We were already past the point of no return. So we have work to do, and it's just to shift the goal. I apologize for the long answer.
Thank you.
So one more question from the audience. Go ahead, Susan. Sorry.
I just wanted to say, both of you have confidence in atmospheric methane removal, which is why you're devoting all of your energies to it. Could you just give a brief word on your confidence about this and why we should care about it and pay attention to it?
Yeah, it's a brutal question, Susan. We know the science works. We know that the iron salts can catalyze methane. We know that's the quickest way of reducing the radiative forcing of the atmosphere. Will it work? We don't know. We genuinely don't know. But it's the best thing that we've got at the moment. Or perhaps there's a suite of other interventions like solar radiation management. And it's a bit like being on the Titanic. If the Titanic has sunk and there's some life rafts in the water, do you swim for them or do you just give up?
Peter, would you like to weigh in on that?
Yeah, I'm 100% optimistic. And the reason why is we have smart people involved. And so we know that nature oxidizes methane in the atmosphere. And there's no reason to think that we can't at least do as well as nature and perhaps 10 times better. Now, it is true, as Kevin says, that our current plans will probably not work as planned, that just like building a house, taking a weekend trip, it never goes exactly as planned. So we know it won't go exactly as planned, but we also know that we're not going to give up. Just, again, if I'm taking a weekend trip and I'm determined, I will take a weekend trip, even if it's a staycation in COVID times. So yeah. I'm 100% certain that we'll do it. It's been done. We will find a way to do it. And currently, no one is proposing any serious reason that our current plan won't work. The only skepticism is that it hasn't been done yet, which is true, and we will do it.
I think just finally closing off on that, it's such an important question. Is that we have a moral imperative to give it our absolute all. There's no point, actually debating is it a 1% chance of success or a 99% chance. We are, if we think there is half a chance, if we think there's any chance, we have no right not to try our hardest, and that's where I sit on this. If there's a chance, we must go for it now, and give it full energy and full force, and that's it at the moment. We are the only place in the universe that we know that there is life, and we need to make sure that we preserve this higher life form that we have created, and we have an obligation to do so. We are the consciousness of the universe.
That's beautifully said, Kevin and Peter.
If I can add, my daughter Erica likes to present it this way, that if you look at the future scientifically, you can predict the probabilities. If you look at the future as an engineer or a project manager, you say that we're going to do it. We're not quite sure what the pathway is. And so the difference between what Kevin is saying and what I'm saying, I think, is that Kevin is saying, given what we know, the pathways we know are 99% sure to work. And I'm saying that even if the pathways we know don't work, pathways that we will discover in the next year or two, we'll find the one that works for sure.
Wonderful.
So all good things have to end at certain time. And I know we are enjoying the discussion, but we have passed 13 minutes. I know the speakers, they have to also have their other things to do, and the audience also thinking about, okay, maybe when this is going to end. I'd like to thank Susan for moderating, and absolutely a lot of thanks to Peter and Kevin for coming, taking their time to enlighten us with this problem that the humanity is facing today. And with that, I just want to say a few words that this webinars we do, please come back again. We do this to create awareness of the problems, as well as we want to show that there are solutions that we can take, just not the problems. The climate change is threatening the humanity today. And that's one thing I want to take away from this. But at the same time, there are the solutions to solve this. And I want to take that away also at the same time. The way you can help is to talk to another 5 people. Just what are you learning? There are problems in this world and there are solutions. And with this, I want to see at some point there are enough people that people are aware and talking about this. There are national, international conversation. And that is the time I see the government is changing the policies and in a big way that can make the survival, the flourishing of humanity possible in the future. Thank you very much. Thank you everyone for attending. Have a nice day and good night.
Thank you.
Thank
Thank
you.
you all. Thank you. Thank you.